So today I will speak about Brauer-Siegel theorem and analogues for other varieties. This was actually one of the themes of Alexei's PhD, and a lot of his work was dealt with that. As a personal recollection, he introduced me to many aspects of Russian culture. And since a speaker is a kind of guide for a small moment through a small chunk of mathematics, and I remember once going to some distant place in Moscow with Alexei, and he said to me, I will be your Ivan Susanin. So apart from Russian people, probably people don't know who Susanin was. He was a legendary Russian guy who is famous for saving the Tsar and Russia in the 17th century. It's a legend. He led the Polish army through the forest and lost them in the forest and never reappeared. So I hope I won't be your Susanin through Brauer-Siegel theorems. So there will be 3 topics which I won't have time to cover all of them in details, but of course, well, the first one will be number fields. So that's the classical Brauer-Siegel theorem. There will be something about surfaces. So that's analog of Brauer-Siegel theorem for surfaces. And the third topic will be elliptic curves, Abelian varieties. So perhaps I'll give right away the name of people who contributed. So here, of course, the Brauer-Siegel theorem is a statement about number fields. There is, after that, there is a deep contribution from Tsfasman and Vladuts, and of course Alexei. For surfaces, it is a recent contribution of Richard Griffon. And for elliptic curves and Abelian varieties, well, there's 2 directions. First, there's the work of Kunyavskii and Misha. There is also some work of Alexei, of Griffon, and myself with Hindry-Pacheco. So perhaps I will sometimes forget to mention the names, so I wanted to give them right away. So what is, well, before stating exactly what is the Brauer-Siegel theorem, what is the common feature of all these topics, the idea is to, well, to each of these situations, there is associated naturally a finitely generated group. For number fields, it's the group of units. For surfaces, it's the Néron-Severi group. And for elliptic curves Abelian variety, obviously it's a model Veil group. So we want to, well, measure the volume of a finitely generated group. And of course, when I mean measure, I mean individually there's practically nothing that can be done except computing examples. All this theory is asymptotic. What can we say for a family of number fields, a family of surfaces, a family of elliptic curves? And we'll discover that to measure this volume, we have to measure also something. We have to measure so the size of, I will call it the associated local global abstraction group. So in case of number fields, it will be just the class group. For surfaces, it will be the so-called Brauer group. And for elliptic curves and Abelian varieties, it will be the Shafarevich state group. And really, the idea behind the Brauer-Siegel theorem is that you have to, it's much better if you do both at the same time. If you try to measure only one, it's too random, you don't get anything interesting. So having said all that in a general setting, I will now quote the classical Brauer-Siegel theorem. So we take a number field. And as mentioned already, we're interested in asymptotic theories. That is, we take actually an infinite family of number fields. So we have, well, the class number, which is in many ways a local to global abstraction. I mean, all ideals are locally principal, but not globally. And actually, well, later I will quote that the class group can be also described as a Shafarevich state group associated to units. Then we have the regulator. I mean, I think I don't have to recall this. The unit can be embedded as a lattice in some canonical vector space. And essentially, the regulator is the volume of that lattice up to a small factor. And then we have the simple measure of the number field, which is the, well, I will take always the absolute value of the discriminant. And the Brauer-Siegel theorem says that actually, well, roughly speaking, the product of those two is equal to the square root of delta. So I will write this in three ways. Well, the first way is loosely speaking, so I will write it like this. This is the square root. So more precisely, what it means is that, well, there's two ways to formulate it. Is that you can, this is smaller than some constant times delta k, 1/2 plus epsilon. And this is larger than, well, another constant delta 1/2 minus epsilon. I will state precisely the conditions for that. Another way, which is the one that I will really use later, is to say that, in some sense, the limit of the log of hk k over log of square root of delta is 1. Here, of course, the limit is implicitly there's a family, that is when the discriminant goes to infinity. So there is the strategy for all of this. So what are the conditions? Well, let's say Brauer-Siegel 1 will be just, I mean, I take a family with, of number fields with fixed degree. Then this is absolutely unconditional. You can get better bound here. Instead of delta to the epsilon, you can put a power of log delta. The lower bound is actually the really difficult part. And the generalized Riemann hypothesis, or even much weaker than general Riemann hypothesis, you can get lower bounds like this, delta square root of delta over log delta in this lower bound. Actually, you don't need the full Riemann hypothesis. Exactly what you need is, well, if I put here 1, if I draw the critical strip, the only thing you know, it is known that if I put a small, if I take a small disk of radius 1, sorry, center is at 1 over delta, it is known that there's at most 1 0 for the zeta function, at most 1. And so, of course, the Riemann hypothesis says that all those zeros should be on this line. So if you believe the Riemann hypothesis, this is an absolute certainty. But no one has been able to show that there's no real zero there. There's only one, if it exists. So if that zero is which is called the Siegel zero, doesn't exist, then you get this much sharper lower bound. So only a tiny bit of Riemann hypothesis would be enough, but we don't know how to prove that. So a broader condition is if we relax the condition, I mean the degree of the number field can go to infinity. There is a condition that's absolutely necessary, so I've called dk, maybe I will call n, sorry, the degree. If you suppose that the limit of n over log delta is 0, so log delta grows at least proportionally to n. For example, in a completely unramified extension, they are proportional. So this limit is not always 0, but it is very often 0. And then you have to put some more condition. Either you use GRH. Again, I mean, it is enough just to have no Siegel zero, but for all extensions. Or you impose, suppose you have, it is easier to state it with a tower of number fields. In the classical literature, it's you suppose that all the ki's are normal extensions of Q. But precisely, Alexei had shown that the condition that just this extension, this tower of extension, is normal, or in other sense, you can build a tower where each step is a normal extension. This is, of course, much weaker than asking that the whole extension to be normal. Then this still holds. Before going into Misha and Sergei's work, perhaps a comment. The most striking part, if I give an example, is for quadratic imaginary K. Of course, what it says is that, I will write it this way, that the class number grows very quickly to infinity. It grows like the square root of d if d is the generator. Of course, the Brauer-Siegel theorem is not effective, so it doesn't allow to compute, for example, fields with class number 1, but it does tell you that there's only finitely many. For real quadratic, this is in some sense even more interesting. There's only one generator of the group, so what it says is that and this is really the typical Brauer-Siegel behavior. What it says is that maybe the class number is small, but in that case, the generator of the group of unit has to be huge. Or maybe the unit is small, but then the class number has to be enormous. This is really the behavior that's observed. I mean, it's not an artifact. It is rather easy to construct sequences of quadratic fields with small units. So you have infinite sequences of real quadratic fields with class number roughly equivalent to square root of d. The other way around is conjectured, but totally unknown. I mean, it's even conjectured that there's infinitely many quadratic fields with class number 1. But it's not even known if there's infinitely many with bounded class number. In that case, the unit would have to be enormous. The next step is really a very deep analysis of this condition by Misha Tsfasman and Sergei Vladuts. They discovered the following. I will state it that way. If you, well, I'll define the if Q is a power of a prime, and you have a sequence of fields, I'll define the density. This is the limit. For the field. I would say, suppose we have a sequence of fields. It's the limit of the number of prime ideals of Ki, which have norm equal to Q. The limit of that over the log of the square root of the discriminant. Of course, the limit doesn't always exist if you take any sequence, but if you take a tower, this limit exists. And if you take any sequence of number fields, you can always extract a subsequence that's all of those limits exist. So they are a very good measure. Of course, under this condition, the limit is 0. That's an easy exercise. And the deep fact that Misha and Sergei discovered is that you still have, under more or less the same condition with that, you still have a Brauer-Siegel theorem, but the limit is not 1. The limit can be expressed with those phi q's. I will write the formula. Say under GRH, then there's just no condition except that you take a sequence where the limit exists. And in that case, the limit of this Brauer, what I will soon call the Brauer-Siegel ratio, so is 1, but plus correcting terms. You have the sum of those phi q's log of q over q minus 1. And you have, well, I didn't define them, but it's easy to guess what they are. If you take the real places, it's the limit of the number of real places over that. I call it phi r. This is log 2 and minus pi c. Log 2 pi. So actually, you can make computations, and of course, there are examples where the limit is not 0. Still, I mean, you can write an explicit interval where they all lie, and perhaps some of the most interesting examples are the infinite unramified towers constructed by, first constructed by Golov and Shafarevich. And you can try to compute the limit for that. And there are examples where this limit is not 1. Well, it's more or less obvious from the formula that it won't be 1 in general. In fact, it's extremely unlikely to be 1 if any of the phi q is different from 0. And if there's only finitely many, actually, even Baker's theorem will tell you that it's never 0. This has quite a number of impressive applications to algebraic number theory, as asymptotic algebraic number theory. So I will refrain from going too much into that because I want to treat some of the other two topics. I will just mention what is...
May I ask a question about this?
Sure.
So here your assumption was that all of these limits exist.
Yes.
For this level.
Okay.
So all the phi q and the phi r.
So,
the assumption for this last equality was that all the phi q exist.
yes. Well, the thing as... so?
Yeah. Well, that was the statement. Yeah.
Yes, yes. I mean, okay, the limit, I said it, I think, verbally. The limits, so there's various limits. The limit exists if you take a tower. That's essentially an exercise, and that's it in Misha and Sergei's paper. And so it's not such a strong assumption. And the other observation is if you take, let's say, a random with discriminant going to infinity, then you can always extract a subsequence where all those limits will exist.
Okay, so but the statement is that it holds for any sequence and any sequence of fields for which the limit exists.
Yes, yes. And if
you don't assume that the limits exist, can you take if you take the difference of the left-hand side and the right-hand side, can you say that where the phi q's are not constant, you get a function?
Then you should take up and lower limits, and you get inequalities.
yes, I mean.
Same without GRH.
The thing is, I mean, if you look at all the subsequence that you can extract for which it will converge, it might give you different values. So the upshot is that you remain in a certain fixed interval, but it's hard to say anything more. I don't know if you can say anything more.
Well, we can give some explicit bounds, but there are some explicit bounds, but without GRH as well as without the existence of these limits, it becomes much less beautiful.
Mm-hmm. And sorry, I will also, I mean, there is an unconditional version where the hypotheses are exactly like that. I mean, you have, so it doesn't, it's not interesting to take bounded degree because that's all already covered. The limit is always 0. But if you use Alexei's hypothesis that the tower field extension, each step is normal, then you don't need GRH for this. The hypothesis is the same. So I will just explain before going to an analogy. The strategy of the proof of this is, well, basically in 2 steps. The first step, you have the class number formula. So I've already mentioned the zeta function. So you have Dedekind zeta function. I will at least write. So it's a product of all prime ideals of 1 minus the norm of P minus S minus 1. And the class number formula tells you what is, well, the value. I will write it like this, zeta k of 1. This means just the first non-zero Taylor coefficient. In that case, it's the residue at S equals 1. Well, this has a beautiful formula, which on purpose I will write like this. It's the class number times the regulator over the square root of the discriminant, and times small terms. So small terms that I will write like this, 2 power r1, 2 pi power r2, over, so I will write in a fancy way the number of root of unity. The number of root of unity I will write as the torsion group of the multiplicative group. Of course, it's for analogies that I write it like that. So this is the first step. So that's an old theorem. And it's easy to see that you need then estimates, analytic estimates. Well, that will tell you that this value is never very large and never very small. So here what you can get is, well, you can get something with log delta to the degree -1. And here, well, this is the really hard part. You can get delta minus epsilon, that's Siegel. And if you have GRH, you can get, well, with GRH, you can get 1 over log delta. Well, constant. That's a constant. So, of course, I give absolutely no details, but really there's two basic parts. One is an analytic formula, the magic of zeta function, that, I mean, you build with more or less trivial local object. You build a global zeta function, and you expect that the values or the behavior reflects deeply the arithmetic of the global arithmetic. So this is a wonderful example of this principle. And then you have to use essentially complex analysis to estimate this. This being, of course, the very hard part. So I think that's all I will say for I want to go now to, well, to surfaces. So actually, things about abelian varieties and elliptic curves were developed before analogues. So also, I want to say, I mean, all this part has analogues of function fields that I will not develop, that are in some sense simpler, but that are quite deep. I mean, they include Riemann-Vladuts bounds, this kind of thing, which is probably well known, better known to most people here. So on surfaces, well, I will simply quote, of course, you can make general conjectures, but we don't know how to prove them. So I will quote a case where we know how to prove things. So this is the work of Richard Griffon. So he looked at the example, well, it's a simple surface which is indexed by a number d, which is called the Fermat surface. So it's, well, the equation is simple. So it's a projective surface. And what we look at here is actually people have been trying to compute the Néron-Severi group. So the surface so the Néron-Severi group, to state it easily, essentially is the quotient of, well, linear combinations of curves, well, curves on the surface, well, modulo algebraic deformation. So it's a classical algebraic geometry theorem that it's true actually for any variety, that this is a finitely generated group. So in that case, there is, of course, to measure what I call the volume, we need some measure. So there is an intersection pairing. I mean, it's classically, you can define the intersection of two curves. So if the curves intersect properly, it's just the number of points. And by deformation, you extend that to all curves. So what will be the regulator of this? Well, by definition, it will be the determinant of the Gram matrix you can compute with a basis. So let's say if I tensor with Q, then this is just a vector space with some rank rho. And I take the determinant. It doesn't, of course, depend on the basis. And I take the absolute value because it's, the pairing is not positive definite. There's 1 plus and the rest is minus 1. And actually, for many reasons, it is important to know the size of this regulator. In some sense, it tells you how complicated is the geometry of the surface. And, well, if you try to compute alone the regulator, again, it's very irregular. But if you introduce the analogues of the local global obstruction, which in that case would be the Brauer group, so that I will just put a fancy formula. Well, it's something that measures local to global obstruction. I won't go too much into details. Then, if you group together those two, then you get a very regular behavior. That's the statement of Griffon's theorem. I will state it like I stated the Brauer-Siegel. So the analogy will be, I hope, clear. So the cardinal.
Over what field are you working?
Sorry?
Over what field are you working?
Oh, sorry, I didn't mean. Okay, here the field, sorry, is a finite field. Yeah, otherwise, otherwise it's not known that the Brauer group is finite over FQ. I'm working over FQ. Sorry, I said in the beginning that I would shift from number fields to function field or finite fields, but I should say some to what I switch. So if you take the cardinality of the Brauer group times this regulator, regulator of Fd, and you divide by what would be, the analog of the discriminant is Q to the power, the geometric genus of the surface. This goes to 1. Like for the Brauer. So I hope at least formally the analogy is clear. What is also similar is the strategy. The strategy is to study the zeta function of the surface and prove essentially there's a conjecture of Artin and Tate that relates the value at t equals q minus 1. So here, this function, of course, you should always think that for analogy, you should always think of t as minus qs. So the value at 1 is the value at q minus 1. There's a conjecture of Artin Tate, which has a really a similar shape that relates to those 3 quantities. So the strategy is to use this Artin Tate conjecture, which is a theorem in this case, with analytic estimates for this. It is, as I will explain in more detail over elliptic curves and Abelian varieties, what seems to be really a general feature is the upper bound. That is, that the limit sup is certainly, for very general reasons, always less or equal to 1. It is much less clear in general that the limit inf will be also 1. But in this case, it is true through explicit computations. I think it's a very nice result. So I will finish by speaking on abelian varieties, and so that would be the third part. So I've kept the class number formula. So in this part, I take A, an abelian variety, over K, a global field. So in that case, I want, to a certain extent, to treat either a number field or a function field, by which I mean the function field of a curve over a finite field. Then the analogy, well, before perhaps giving the analogy, well, I'll write the Brauer-Siegel formula under this one, and hopefully this will make absolutely clear what is the analogy. So we have an L function, well, which is again defined by an Euler product. So I will write it like this. To make the notation compatible, I take the determinant of 1 minus the Frobenius at V, Q, V minus S, and here I take the dual of the Tate module, or H1 of A. I have to put so that the formula works also for bad primes, I had to put the fixed part by the inertia. And the Brauer-Siegel conjecture relates the value at S equals 1 to the quantities that will be interested. So I write first the formula, and I will explain what each term means. So the BSD, well, there's a difference, is that it's a conjecture, not a theorem. What it says is that, the value, the first value at 1, which in that case is the limit over S minus 1 R. So if I take the analytic rank, it makes sense. Of course, it's part of the conjecture that this analytic rank is the rank of the model vein group. This is the cardinality of the Shafarevich state group times the regulator. So that's the regulator defined by the Néron-Tate height over, so to cover both cases, I will call this H tilde, and I will explain what is H tilde. And then we have, terms that are supposed to be small, but it's not obvious that they are small, which is the Tamagawa number and the number of torsion points, on A cross the dual of A. And of course, I gave this fancy formulation so that the analogy would be a bit closer. Now, let me define quickly what are all these terms. First of all, there is something classical which is called the height, the exponential height of the abelian variety. So in the number field case, this is just the exponential of the Falting's height. won't go further into that. And for function field, it is the exponential of the height that is the analog of Faltings that was defined before by Parshin, which is the degree of the relative differentials that I will write like this. So for an elliptic curve, so this is, of course, the function field case, and here the number field case. Well, in the function field case, the height of an elliptic curve is just q, the degree of the minimal discriminant over 12. So it has a simpler expression. It's easy to compute. So what is this h tilde? Well, in the function field case, it is exactly the height that appears in the Birch-Newton-Dyer formula. But in the number field case, it is actually a different quantity, which I will just write like this, which is the inverse of the real period of the Abelian variety. But, well, one can show that, loosely speaking, it behaves exactly like the height. So it's not exactly the height, but for our asymptotics, it behaves as if it was the height. So this is the analog of the square root of the discriminant. Now, those terms are a bit complicated. It's much harder to prove. See, it's easy to see that those terms are both quite small. I mean, in terms of the asymptotics. It's not at all easy to see that those are, but it is true. It's actually one of the things that we prove in the paper with Pacheco is that this Tamagawa number is smaller than the height to the power epsilon. It is an integer, so it's greater than 1. And the same is true for the number of torsion points. So A. So this is not trivial at all, but it's true. And it's true for number fields and function fields. Now, once we know that those are neither small, neither big, we would like to estimate, of course, the value of the L function. So the value of the L function, well, I will state it simply. If you have the Riemann hypothesis, this is smaller than the height to the power epsilon. So for function field, of course, the Riemann hypothesis is not a condition.
Evaluated at some point?
Sorry? At the point 1. At the point 1. So this special value. So for function field, it's a theorem. The situation of the Birch-Newton-Dyer conjecture, of course, for the number field is not satisfactory. There's a finite number of elliptic curves for which is fully proven. So when you want to do asymptotics on a finite number of things, it's not very, well, it cannot be unconditional. Over a function field, the situation is much better. There is a whole series of papers, well, starting with Tate, Milne, and ending with Cato, Trian, which you can formulate like this: if SHA, or even one of the components, is finite. So this is the function field case. If SHA is finite, then BSD is true. And further, there are many ways to show that SHA is finite. It's not known in general, but I mean, you have also the equality of the rank is enough to show that SHA is finite and all that. And the equality of rank for example, you have to show, if you take an elliptic curve over a function field, you have to show that the surface satisfies the so-called Tate conjecture. So, for example, if the surface is rational or is dominated by a product of two curves, and all these things are true, and that gives a lot of examples where the full Brauer-Siegel conjecture is known. Anyway, accepting the Brauer-Siegel conjecture or doing it for families. So we can prove unconditionally a Brauer-Siegel theorem for families of elliptic curves. For example, the first one we devised was the following family of elliptic curves plus y equals x cubed plus td. So, of course, over k equals fq of t. So, well, to avoid problems which suppose that the characteristic is different from 2 and 3, and that d is co-prime with 1, then we can show unconditionally that the limit, so that I will call the Brauer-Siegel ratio of log of Tsfasman-Vladuts Tate group times the regulator over log of the height, that goes to 1. There are many examples that were computed by Richard Griffon, for example, the so-called Legendre curve. The same thing is true. And further, it's easy to compute at least the asymptotic of this height. And it tells you that this product grows in some sense exponentially with d. It's proportional to d. So it tells you that either the regulator is very large or the Tsfasman-Vladuts state is very large. So in some sense, I said in a provocative way, that explains why it's difficult to compute the model Veil group. Of course, it's a vague sentence. I will conclude by asking a question which is actually the question that really fascinates me in this business is, so if you have let's say, if you have Brauer-Siegel and the Riemann hypothesis, which most of you probably believe, so I will write it like this, BSD plus GRH, so both in function field and number field case, implies the following, that the product, the Tsfasman-Vladuts group times the regulator, is smaller than C epsilon, the height, power 1 plus epsilon. And further, those examples show that actually you have another, for some families, you have the reverse inequality with minus epsilon. Now, you notice that I don't write the one on the other side. I don't write the full Brauer-Siegel theorem. And this is, well, I thought about it for a long time, and I end up believing that actually it's false. Though I don't have any proof of that, and I have only heuristics. And perhaps, how much time do I have left? Okay, I'll have 3 minutes. I will state it like this. So we have the limit, well, I will write for short this quantity, I will call it the Brauer-Siegel ratio of AD. So I will speak of the Brauer-Siegel ratio, just for short, not to write the log of SHA times the regulator over the log of the height. That, well, the limit sub of Brauer-Siegel of A over K, well, at least if we grant finiteness of Char and for the number field case, for the full Birch-Thornton-Dyer conjecture and Riemann hypothesis, we've proven that the limit sup is 1. Okay, the limit sup is less than 1 because of that, and it is 1 because there are some subfamilies for which the limit is 1. So a limit sup is always greater than a limit inf. That's trivial. But, okay, I want to explain why I think the limit here should be 0 and not 1. Well, there are two reasons to expect differences. Perhaps I should have mentioned that earlier. If I redo the drawing, in the number field case, we had the critical strip, and, well, if you believe the Riemann hypothesis, all the zeros are on this line, and we're looking at the point 1. So certainly the zeros are far away, even if we don't know how to prove it. They are certainly far away. In the case of abelian varieties, the situation is slightly shifted. Well, if you don't normalize, of course, the L function. Well, whatever you do, the critical strip is centered at 1, and you're looking at the value at 1. So the situation here is different because you have all the zeros on this line, well, at least so you believe it's true over function field, and you believe it over number fields. So actually, you have a lot of zeros very close to 1. So it's very debatable if you're asking for the values of this function, which has zeros very close. Can it be very small, or is it always, it becomes quite dubious. And basically, the argument, the heuristic argument that I have uses a result of Valls-Purget. Actually, I will set it over number field, so it's over function field. Sorry, the over function field. It's been worked out by Antug and Zimmermann. It says the following: suppose you have. Well, I will state it with an elliptic curve. You start with an elliptic curve, and you twist. So the elliptic curve is y squared equals f of x, and you twist it. So I work over fq of t. You twist it by a polynomial d of t, y squared equals f of x. Then what Valls-Purget tells you is that you can express the value at 1, not the first derivative that doesn't vanish. The value at 1 is, well, there's a small constant that I will forget. There's a Fourier coefficient square over the square root of d, where C, N are the Fourier coefficient of a weight 3/2 modular form. So there's plenty of them that vanishes, but we look at those who don't vanish. You have, well, the equivalent of which is a theorem of a function field, that this is smaller than d1/4 plus epsilon. This is the analog of the Ramanujan conjecture in this context. And you're asking, I mean, the non-zero coefficient, either they are all roughly of that size, or they behave like the coefficient of a nice modular form, that is, they take almost all values between 0 and the maximum. Well, okay, the distribution is not known. There are conjectures for it that fits with that heuristic. The idea is, if you look at also numericals, there's plenty of values that are very small and non-zero. So if, I mean, let me state it like this: if those coefficients are all that are non-zero are greater than d1/4 1/4 minus epsilon, then the limit is 1. But that looks extremely unlikely. And I mean, when I've asked to people who study those modular forms, they told me there's no way this is going to happen, though it's not known. This is the most convincing heuristics that I have to guess that the limit should be 1. But it's an entirely open question.
You mean 0?
0, 0. I mean 0, yes, sorry. So I think I will stop here.
Is there any questions for Marc? No question? So if not, we write on schedule.
I have a quick question. So do you expect that there will be things in the middle? So do you expect there will be values of or limits between 0 and 1, strictly between 0 and 1?
Well, yeah, but for silly reasons. I mean, you have, again, on this thing, you can show that the limit sup is 1. So if you have a subsequence that goes to 0 and another subsequence that go to 1, you will have other subsequences but it's not very interesting. Yeah, well.
Another question? Yeah?
It's just a comment to that last question that in the function field case, we knew that all the interval for Brauer-Siegel ratio can be realized, that's not true what I'm saying, but that's very close to being true. In the number field case, we do not know even that the ends of the interval we give are realizable. So, and the fact that it is dense or something, it's out of reach completely, even in the function field, in the number field case, which is much simpler than what Marc is speaking about.
Okay. If there's no other question, then let's thank the speaker again.